Hi everyone, welcome back to our continuation of the lectures on quantum mechanics, and this is the second and last lecture for chapter 7. And again, our main reference for this lecture is Introduction to Quantum Mechanics by David J. Griffiths, and this book is highly recommended for you, so get hold of a copy of this item. So to start with, our session would start with the hydrogen molecule ion. So we will be estimating the energy of this quantum mechanical system. So we're now looking into a hydrogen molecule ion in which there are two protons and only one electron in the system. So in this case you have a proton here and another proton here separated by distance r, and one of the protons is holding the electron. So in this case you can treat this as a hydrogen and this one is a proton, or you can also treat this as the hydrogen and then you have a proton here. So you can interchange the proton with the electron. So in this case, the trick is that you have to try a trial function which is symmetric between the two protons. So in this case also, you have the electron is, of course, they are separate. The protons are separated by r, and one of the first proton should be at least an r1 distance with the electron. The other one should be r2. R1 could be greater than r2. R1 could be less than R2, or it could be that R1 is equal to R2 as well. So we proceed. Interestingly, one of the byproducts of this calculation is to calculate calculation of the actual value of r, which is the separation distance between the two protons. The Hamiltonian of the system would be this is the kinetic energy of the electron, and this one is the interaction of the electron with the first proton and the interaction of the electron with the second proton. So again, I'd like to repeat that. This is the interaction of this is the interaction between the electron and the first proton, and this is the interaction of the electron and the second proton. So again, in this case, there's only one electron and there are two protons. So you can treat one system as a hydrogen atom and the other one as just a pure proton. So you can treat a hydrogen atom in its ground state, and then you bring in a proton from far away and putting it fixed on a distance r with the other proton. So it is assumed that or we should be able to assume that the proton, the distance between the two protons should be greater greater than the Bohr radius. So that the electron's wave function would not change very much. So if the two protons are very far away and the electron is near to one of the proton, then its wave function will be just the hydrogen atom's wave function. Also, in this problem, you can treat the two protons equally, so that one could assume the electron, and then you can construct a trial function of the form this psi. This is a non-committal wave function where the electron could belong to the first proton, or it could also belong to the second proton. So here you have to normalize to get A. So this is the normalization. So of course this one is also 1, and this also is equal to 1, but this one we have to elaborate the third term there in order to get A. So the statement is the first two integrals are just equal to 1 since phi g are normalized, but the third one isn't. Anyway, going back, you have here your trial function psi, which is a combination of two wave functions. The first wave function is that the first proton owns the electron, and the second wave function is that the second proton owns the electron, or proton 2 owns the electron. So the third integral would look like this, which is just this using the hydrogenic wave functions. So it would just be that expression. To simplify this integral, we can set the first proton on the at the origin, and then the second proton, which is just r away from the first one. So you can put the two protons in the z-axis such that your r would be just lying along the z, and of course your r1 would just be r, and then your r2 would be square root of r square plus capital R square minus 2r capital R cosine theta, which is where the theta is measured here. And so this is like a spherical coordinate system, so you can use spherical coordinates here to solve the integral. And so by the way, this is using cosine law. So based on the figure, you have r1 equals r and r2 is equal to this expression. So you can rewrite the I, this one here, you can rewrite this term to this one, So again, here the integral for phi is trivial because you're considering all space. So phi would just be 2 pi. And you can let this one here, you can let this quantity to be equal to y, so that you can square it and get the derivative of it and be able to get this expression. And so your theta integral would be just here, would just be this one. And so we have to be very careful with the limits here. This absolute R minus capital R, and this is R plus R. This is the minimum value of R minus R, I mean capital R. So if you evaluate the theta integral, you'll be able to get this expression. And now, having that result, you'll be able to rewrite the I in this form. So there are now 3 terms, this one here, this one, and this one, because of the result here. So anyway, you have that. Evaluating the integral and doing some algebraic simplifications will arrive at this one here, this expression for I. Remember, this is the third term in the normalization of psi. This is equal to 1. By the way, this I is called the overlap integral. It measures the amount by which psi g r1 overlaps psi g r2. And note that the value of I goes to 1 as R goes to 0, and it goes to 0 as R goes infinity. So in terms of I, the normalization factor would be, because I is a very long expression, you can rewrite your normalization factor as that one. Now we're ready to calculate the expectation value of our Hamiltonian with the given trial function. So this is now the Hamiltonian for the, this is the Hamiltonian for the hydrogen atom, and this is the Hamiltonian for the hydrogen molecule, ion. So now you have you're applying your Hamiltonian to your trial function psi. Your psi is just equal to this one here, and of course your h would be this one here. And then when you do it, this is just This one is just when you apply this one here to here, which is just this one, this one and that one. So you will have your E1 psi here, and of course your this is your, the whole thing actually is, let me just erase that. The whole thing, this one is your psi, so it will just give you E1 for that because of this thing here. It's the E1 is the eigenvalue of H. So you're left with this part. So it follows that your expectation value of H would be this one here, because you have to remember that H is just equal to psi H psi, and that is equal to integral of psi star H psi star dx, and your psi is just actually equal to a psi g r1 plus psi g r2. So that's why you have this one and this one. So you can name the first one as the direct integral and the other one as the exchange integral in terms of dnx. So if you solve problem 7.8, the results would give you d as equal to this one and your x equal to this one. We will not show the solution, but let's just, it's not bad to accept these results if you have just solved 7.8. I mean, to prove the results, you have to solve problem 7.8. But anyway, it's not really bad to accept the results for dnx. So putting all the results together and recalling that your E1 is just of this form in the discussion of the hydrogen atom, so it will give us the expectation value to be of this form. So remember here that your D should write as this one, and your X write as that one, and your I you'll have to write as this one here. So it's longer when you write the expression with the ones given in equation 7.47, 7.48, and equation 7.42. So just to shorten the expectation value, we'll just write this in terms of d, x, and I. And your E1 is again just the energy of the hydrogen atom, the ground state energy of the hydrogen atom. But also, there is a potential energy associated with the two proton repulsion. So, and it's just that one. And by the way, according to the variational principle, the ground state energy is less than the expectation value of H. So by the way, if you express the total energy of the system in the units of negative E1, and of course expressing your R over A to X, then you would have this expression. So by the way, this would be equal to negative 2 over X E1 then. So anyway, this is very you can arrive at 7.51 by doing some a little bit complicated algebra. So here we can see the plot in the next slide. So evidently, bonding between a hydrogen atom and a proton occurs, and it is in the region which the graph is below -1. So this indicates that the energy is less than that of a neutral atom plus a free proton. And we can actually get the equilibrium separation of the proton to be about 2.4 Bohr radii, or this is 1.27 angstrom. And here you have the plot. So it occurs, the bonding occurs somewhere here, this point here. So it's equilibrium at that state, and it bonds, the hydrogen bonds with the proton, forming the hydrogen molecule ion. So this is very important. So if you do some calculations, the graph is always important. So if you have time, you can evaluate this problem 7.8, problem 7.9, and of course 7.10. You can screenshot them and solve when you have extra time. Seven point 14, 7.15, 7.16, 7.17. There's a lot. So that is all for this chapter. I hope you've learned something, and hope to see you in the next chapter.